Let's start again. Now we have Haroldo Junior, that is going to talk about black holes immersed in strong magnetic fields. So, Haroldo, the floor is yours.
Thank you, Antonio, for the introduction, and thank the organizers for the invitation to present this work here. My seminar today is going to be about magnetic fields and black holes. This presentation is based on this work here that was published in 2021 with Pedro Cunha, Carlos Herdeiro, and Luis Crispino. So, just to break the ice and start the conversation, I'm from Belém, but I'm working at Maranhão, at São Luís, which is a beautiful city. This is São Luís, and this is also São Luís. This here is at the Lençóis Maranhenses, and this is Carolina. So, you are all welcome there. The problem is that I am starting a career, so I don't have the money to fund your visit. But since the euro is 1 to 6 reais, I think this is not going to be a problem. Okay, so what's the outline? What is this presentation about? It's about black holes and magnetic fields. By the end of this presentation, I want to answer these three questions here. Why magnetic fields? How to model magnetic fields around black holes? And what are the effects of these magnetic fields around black holes, in particular when they are strong? And to begin, we all know that the Kerr solution describes an isolated black hole, an eternally isolated black hole that have never interacted and will never interact with anything. It's isolated in vacuum. However, the astrophysical scenario, additional ingredients can play a role. For instance, accretion around black holes. This accretion can play a role. Dark matter halos, and also magnetic fields. In particular, this picture here was obtained by the HT collaboration and show the magnetic field around the black hole obtained by the polarization of the light. And magnetic fields around black holes they can have interesting impacts to the physics around black holes. For instance, with the Bland-Forstnagel mechanism, which is a mechanism for extracting energy from the black hole. So now, how to model these magnetic fields around these black holes? So one possibility that we can take is a pragmatic one, is to consider magnetic field around black holes and use general relativistic magnetohydrodynamics and evolve everything numerically. However, this can be non-accessible to the community. Moreover, this can be also computationally expensive. So some analytical results are not clear because we all have output numbers there. So we can take another approach, another perspective, which is analytical approach. A first analytical approach that we can take is to consider the magnetic field around the black hole as a test field. So it does not have a back reaction in the geometry. It's just there around the black hole. So this consideration it was first done by Wald in 1974. He considered a black hole and he used arguments. He used the Killing symmetries in these black holes to construct magnetic fields. And he obtains, for instance, in the test field approach, a very interesting result. This one here, that due to this external magnetic field, the black hole is going to accrete a charge, which is 2 times the strength of the magnetic field times the angular momentum of the black hole. And for a test magnetic field, this is the Kerr geometry, and here is the solution for the test magnetic field around the Kerr geometry. Now, can we compute the back reaction of this magnetic field into the geometry? So, how can we compute a geometry when this magnetic field is strong to contribute to the background geometry? in order to consider one analytical solution, we have to first study the symmetries of Einstein's equation. But before consider Einstein's equation, I put this very simple example here of the symmetries of Maxwell's equation that we all know here. We all studied Maxwell's equation. So consider Maxwell's equation in the absence of charge and current. These are the equations. We can perform an interesting transformation in which we take the electric field and we map into the magnetic field, and we take the magnetic field and map to minus the electric field. This is a very simple exercise to check that these equations here, they remain invariant. So this does not change. So this is not a gauge transformation. We are taking two different physical systems. So we take one solution and we map in another solution of Maxwell's equation. For instance, we take one solution with a non-zero electric field, and we map. We take a solution with a zero magnetic field and non-zero electric field, and then we map this solution in a zero electric field and a non-zero magnetic field. So we map two different systems that satisfies the same Maxwell's equation. Now, this symmetry can be also extended. In fact, this transformation also maps Maxwell's equation to the Maxwell's equation. Now, does the Einstein's equation also admit such symmetries? So symmetries where we map the fields into another solution, then we map the Einstein's equation to the Einstein's equation. And the answer is yes. And this is in the context of the Ernst formalism. And it's important for generating novel stationary and axially symmetric solution of Einstein's equation. So in order to see these results, we can consider Einstein's equation, Einstein-Maxwell's equation. So we have the Einstein-Hilbert action and the electromagnetic field. So we have here Einstein's equation sourced by an electromagnetic field. And this is the Maxwell's equation in the absence of current and charge. So we can write the metric in the so-called Lewis-Wiles-Papapetrou form, which is this one here. So we write the metric in these cylindrical coordinates, r, phi, and z, and f, omega, and gamma are three arbitrary functions. And we write the four potential for the electromagnetic field as in terms of these two functions here, at and a phi. Then we can write Einstein-Maxwell's equation using these ansatz here. And what we have is these following equations here. These are the so-called Ernst equations. So from the field equation, we have these two equations here. And this capital calligraphic E is the calligraphic E and phi are the Ernst potential. They are given by these two expressions here. So it's the phi is given by this expression, and the calligraphic E is this expression, where a tilde phi is this. So here this nabla is the gradient in the flat spacetime in cylindrical coordinates, and h is this function here. So what's interesting in this form of the Einstein's equation is that the symmetries are more apparent. So similar to Maxwell's equation, we can perform some maps that, for instance, this map here, which is the so-called conjugation transformation. So we take the f function and we map like this. So like to another f bar, omega bar function, and we do the same with omega and gamma. This is the so-called conjugation transformation. What is interesting here is that we map Einstein-Maxwell's equation to Einstein-Maxwell's equation. So we map the field equations to itself. And similar to the Maxwell's equation, we map one solution, one physical system, into another different physical system. In this case, for the conjugation transformation, we can adopt the Reise-Nostrum geometry, and then we map, which Reise-Nostrum is a solution of Einstein-Maxwell's equation. and then we map to this novel solution here, which is the magnetized Schwarzschild solution. This conjugation transformation is not the only transformation, is not the only symmetry of Einstein's equation. There is a group of transformations that the Einstein-Maxwell's equation admits. So this is just one case, which is the one that we are going to use for obtaining the black holes in magnetized environments, black hole in external magnetic fields. So in terms of the background geometry, we map the Rising-Ostrom solution to this novel axially symmetric and stationary solution here. And physically, what we are doing is to map this electrically charged black hole to this Schwarzschild black hole in an external magnetic field, and this magnetic field is constant along the axis of symmetry. Okay, so this is how we model an analytical solution. How it's one way to obtain an analytical solution for a black hole immersed in a strong magnetic field, when the magnetic field back reacts into the geometry. And this is similar, reminds the Schwarzschild geometry. Here we have the Schwarzschild function, but here we have one contribution from the magnetic field, which is this B here, which is the strength of the magnetic field. And we notice here that there is an apparent horizon at r equals to 2m. And this is the same radial coordinate of the Schwarzschild event horizon. Although the radial coordinate is the same, the geometry of the event horizon is not, because this is not spherically symmetric anymore. We break the spherical symmetry in this function lambda here. And this is an embedding of the parent horizon into an Euclidean 3 space. And we notice here that as we increase the magnetic field parameter, the geometry of the event horizon becomes stretched along this vertical direction here. Another property of this solution is that it's not asymptotically flat. Unfortunately, it's not asymptotically flat. As we go to the far region, so we take r going to infinity, we recover this solution here, which is the so-called Melvin solution. It's an universe field with a constant magnetic field along one axis of symmetry. But, well, in principle, this could be a problem because we are not describing something that is asymptotically flat. But we could consider that this solution describes only a region, a near zone close to the event horizon. And we could do a surgery of space-time with one asymptotically flat geometry far from the event horizon. So in order to cure this non-asymptotically flatness. But we are going to study this non-asymptotically flat version to see what's the impact of this property into the shadow and the gravitational lensing, and also in the light rings. So in order to study the light rings, the shadow, and the gravitational lensing, we adopt Hamilton's equation. So the Hamiltonian is given by this equation here. So G mu nu are the components of the metric tensor for the magnetized Schwarzschild solution. And then we can use the machinery of Hamilton's equation. So we can compute the for velocity, the derivative, the for velocity and the derivative of the for momentum. But in order to tackle some analytical result, we can split the Hamiltonian, this Hamiltonian here, in two parts. One is the kinetic part, which is this T here, and the other one is a potential part. And this potential part gives us some qualitative results about the motion of light rays in this magnetized Schwarzschild solution. So this potential part V here, we can write in terms of this L, which is the angular momentum of light, and this E here, and the E is in this eta parameter, which is the impact parameter. And this H here is an effective potential that are going to give us some qualitative results about the motion of light rays in this geometry. So I plot here this effective potential for motion of light in this magnetized Schwarzschild geometry. Here we have the potential computed at the equatorial plane. as a function of the radial coordinate and for different values of the magnetic field. The maximum points, the maximum values of this potential here, the local maximum, they represent unstable light rings. So are closed paths that lights describe. And these closed paths, they are unstable. So any radial perturbation, they tend either to fall into the event horizon or to escape, to be scattered. And here, the minimum, the local minimum of this potential, they represent stable light rings. So the qualitative feature that we notice here for when this magnetic field is small is that we have one unstable light ring here, close to between 3 and 5. And we also have unstable light rings in this case. Another curious feature here is that when the magnetic field is increases, we may have this case here in green, and there are no maximums or minimums here. This means that the black hole for this value of magnetic field admits no light rings, no unstable or stable light rings. So the qualitative result here is that when we increase the external magnetic field, the light rings, they disappear. So we may have a black hole without any light ring. Okay. So there exists a critical value, which we call B critical, such that we divide in two cases. The undercritical case, when the external magnetic field is less than this critical value, there are two light rings outside the event horizon, one being stable and the other one is unstable. And for external magnetic fields greater than these critical values, there are no light ring at all outside the event horizon. And the exact value of this critical value is given by this expression here. So this follows from Hamilton's equation, and we can compute this, which is around 0.18. Now, how can a black hole have no light ring? So usually we know that from Schwarzschild, usual Schwarzschild, Reisenostrom, Kerr, Kerr-Neumann, all the examples that we have that we know, the black holes, they have at least one light ring. So in this case, we obtained here that as we increase the magnetic field, the light rings can disappear. And in order to explain this property, we base it into this work by Pedro and Carlos Herrero, which introduces a topological concept for these light rings. So Professor Herrero explained this in his seminar. So we can associate a topological charge for an asymptotically flat black holes. Essentially, we define this vector field here, and we compute the wind number of this vector field. In the case when we have one unstable light rings, we compute this integral, and the result is equal. The result is -1. So in the asymptotically flat, this vector here behaves like this. So its components, they are in the opposite direction of R. So in this case, the topological charge is equals to -1, which is attributed to this unstable light ring here. And when light rings they appears, they do it in pairs in order to conserve this number here. So we put here -1 and +1, and the final result is still -1. What happens here in the asymptotically Melvin case, and that's why the asymptotically behavior of Melvin is important, is that this same magnetic field here associated with the potential, it inverts the direction. So in the asymptotically flat region, it's in the opposite direction in comparison to the asymptotically flat case. And this implies that the topological charge of an asymptotically Melvin black hole is equals to 0. So since this is a topological quantity, we may have two possibilities. So we may have two light rings, one being unstable and the other one being stable. So +1 -1 is equals to 0. Or we may have no light rings at all, which is just 0. And this explains the absence of light rings in this asymptotically MELV in this magnetized Schwarzschild solution. It's a modification on this boundary condition here at the asymptotic region. Okay, and how does a black hole without a light ring looks like? In order to simulate the appearance of this black hole without a light ring, we applied the backwards ray tracing technique. So we consider here an observer, and we consider a colored sphere with these 4 colors here. And for instance, for Minkowski spacetime, so flat spacetime, no gravitational lensing, the image is like this. So here we map the north. So we are mapping S2 into a plane. So we have here problems at some point, depending on the map that we use. So the north point is mapped into this region here, into this line. The south is mapped into this line here. And here we have these other points here along the image. When we put a black hole and perform the backwards ray tracing technique, we have this result here. So first we have zero magnetic field. So this is Schwarzschild solution. Schwarzschild immersed in a zero magnetic field. The result is this one here. And as we increase the strength of the external magnetic field, we notice here that the shadow becomes more flat here on the poles. So this is on the critical case. And for an overcritical case, a case without any light ring at all, the shadow and the gravitational lens looks like this. So the light ring is essentially marks a threshold between absorbed and scattered geodesics. So when this threshold is not present, all the geodesics along the equatorial plane, they are absorbed. So we see here what we call the panoramic shadows. So along the equatorial plane, the observer sees only a shadow. So everywhere the observer looks, he will see shadow, except one point, which is in the radially outward direction, so behind the head of the observer. And that does not even appear here because it's just one point. And this is what a black hole without any light ring looks like. And I also compute, this is not in the original paper, but I also computed the shadow of a black hole without any light ring when the observer is displaced from the equatorial plane. So this result here is an observer at the equatorial plane, so pi over 2. When we displace the observer from the equatorial plane, put, for instance, at 45, so it makes an angle of 45 degrees with the direction of the magnetic field. So the shadow looks like this. And when the observer is at 30 degrees, the shadow looks like this. So we see here that this shadow has not a Z2 symmetry with respect to this equatorial line here. And also we see these qualitative interesting features like some pixelated shadows in this image here, which is an expression of the chaotic behavior of light around these magnetized black holes. So I hope I answered those three questions that I mentioned in the beginning of the presentation. So magnetic fields, they can play an important role around black holes in astrophysical realistic environments. And we can explore, in order to model these magnetic fields around black holes, we can consider the test approximation, but we can also consider some solutions when these magnetic fields, they back react into the geometry. And we do this by exploring the symmetries of Einstein-Maxwell's equation to obtain novel solutions based on previous solution. In the case of Riese-Nordström, we do this conjugation transformation, and we obtain a novel solution, which is the magnetized Schwarzschild solution, which is also a solution for the Einstein-Maxwell's equation. And what's the effect? Well, strong external magnetic fields, they can give rise to intriguing phenomena such as black holes without any light rings at all, which is a qualitative distinct feature of asymptotically flat black holes like the Kerr one. and we have seen how is the impact of this property here into the shadow of the black hole. So I thank you all for listening to me and also the sponsoring agencies. Thank you.
Thank you very much, Haroldo. So now, okay, I will go like this. So, Uli, please, if you don't mind to come here.
Seems to be working. Well, thank you. I very much enjoyed your talk. I have a very simple question. Going back to the very start, where you argue that the symmetry transformation, or was it E to B and B to minus E, is not a coordinate transformation. Now, I'm not saying that I don't believe you, but I wonder, is there an easy way to understand or see that? Yeah, that one, I think. I think that's that one. Oops. Oh, there we go. Yes, this one. So you argue that it's not a gauge transformation because you change from an electric to a magnetic field. Of course, we know that this kind of mixing between E and B is exactly what happens in the Lorentz transformations. Is there an easy way to see that this is not just a special case of a Lorentz transformation?
Okay, so okay, you have to repeat the question. Okay, so okay, so the question is essentially, is this a can be obtained by a Lorentz transformation, right? Um, well, I had this question while preparing this, and this is well established in the literature. And the argument that I thought at the time is that we can consider a pure electric and a pure magnetic case. So E different than zero and B equals to zero. And I think Lorentz transformation do not map in the one into the other, right? So
So any such transformation has to keep the invariance. And this transformation E dot B changes sign.
yeah, yeah, yes, yes. So one of the scalar is e scalar b. Yeah, yes, e dot b. So yeah, change the sign. Yes, 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 yes. The argument that I thought is to consider the Lorentz transformation of a pure electric or pure magnetic field. You can see that I think we cannot obtain this transformation here from there, if I'm not mistaken. Yeah. Kyle said that the problem of including the source, right? In the presence of currents. Yes, yes.
Okay. Okay, so everybody will have opportunity to questions. I will follow. I will go in order, and then I come back to the beginning, unless it's related to this. Okay.
No, go ahead. Thank you for the nice talk. I have a question regarding the back reaction to the space time because you were mentioned that it's important to have it, but from astrophysical point of view, I don't see why it is relevant to have to include this back reaction. I mean, if you think about binary transistor mergers, the magnetic field is not that big to change the space-time. And if you think about, for example, the matter that we have in galaxies, the 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 matter in galaxies is nothing compared with the mass of the black hole. So what is relevant about to include this by reaction?
Yeah, from the astrophysical point of view, if we put international system here again and we do some estimates, we see that in the astrophysical context, we are in the limit where B is very small. So for B to back react in the geometry, it has to be a very strong magnetic field. So it's in terms of the mass. So we put here in terms of the mass, and I think if well we did this estimative. I think yeah for a yeah yes yeah yeah yes yeah yeah. So in the sense of the back reaction, it's more academic to see these properties. Yes, but in astrophysical, it's better to consider B very small. Yeah.
Good morning, everyone. Haroldo, thanks for your nice talk. I have a question about the gravitational lensing. I think I do not understand well what you said, that there is no gravitational lensing in this model, or just in case there is no white rings. I want you to explain better this part. Thank you.
So, in the case of a magnetized, there is light. There is gravitational lensing. What is absent here is the light rings. So the light rings, they are this closed path that light. So lights close a path around a black hole due to the gravitational attraction. So it's described as circular closed orbit. And what is absence in the magnetized case with very strong magnetic fields is these closed orbits. But the gravitational lens is still there. And it's a non-trivial one because um, these paths, they are chaotic. So light can trace a very complicated path and generate these intriguing features in the image. So this is very far ahead, but let me see here. So these intriguing patterns here. So this image here is like pixelated because the gravitational lens is somehow chaotic. So to answer your question, what is absence in this image here is the light ring, so the closed photon orbit, but the gravitational lens is still here.
So about this figure, what is the direction of the magnetic field in this case? This point. Okay. Okay. So pointing. Okay. So just one quick question about the source of these types of magnetic field. I guess this is kind of a toy model, right? But what would be like a source for this? You are not considering your source, right? This case.
Well, we are not concerned with the problem of where this magnetic field comes from. We are just assuming this model that there is an external magnetic field um, interacting with the black hole. But there are magnetars which have a very strong magnetic field, although not so strong as these ones here. There is also the plasma around the black hole, and this could be sources of magnetic fields around black holes. About your first question, so here is the observer, the north is here. So the magnetic field is pointing south to north. And in the image, so is south to north, so is in this direction here.
Since it's related, comment.
Just to complement Haroldo's reply, perhaps it's interesting that the polarization image of the EHT favors a slightly apoloidal magnetic field as compared to a toroidal one. for which this is a better model. So that's kind of interesting. Of course, it's a toy model.
Thank you for the talk. I had also a question about the image in the hypercritical case. So yeah, you seem to have this kind of two. You seem to have these two so-called shadows around the black hole. Yeah, can you comment on that?
Yes. When we were computed these shadows, we also computed the trace of light that makes this region here. So we trace a path that was a laser that was shot in this direction, and what happens is somehow there is this um, helical path, and somehow this region here is generated by this pattern. So we have this helical path, and then the light ray falls into the event horizon. But a more fundamental answer to why this arises here, I don't have it, because uh, it's more complicated to have analytical results here, because this there is no integrability here. So the motion is chaotic. And yeah, the answer that I have to your question is due to this helical pattern that the light traces around this black hole. But do you have some comment? No, no, just I'm also curious because yes, yes, yeah, yeah, similar to that, yes. But that's because due to the exosymmetry of the magnetic field.
So this would be coming like from east and west, is that right? Kind of. So these circles are kind of at the east and west points that you had on your map, right? Or not? These circles that we're discussing, they are like centered at the east and west direction from your map. Like you had forwards, backwards.
This direction here is the like in the front of the observer, and the west and west. So west and west, they are these points here. So this one here and this one here, if I'm not mistaken. No, this is backward. Yes. So yeah. Oh yes, yes. Yes, yes, yes. In the direction of the west, and yes, I'm more or less in this direction. Yes, yes. You are right. Yeah. Yes.
Yeah, sorry, another quick one is so if you do this kind of stitching to have asymptotically flat, then you should recover light rings somewhere. So you couldn't see these kind of features, is that correct?
If we do that kind of technique to avoid the Melvin asymptotic behavior, there should appear at least one unstable light ring, because the boundary now is the asymptotically flat boundary, uh, and there should be a light ring. Yeah. Hmm. If you do the cut and paste very far away, yeah, yes, 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 you're right. Yes, yes. No, the observer is at 15 m, so 50, it's around the 7.5 the Schwarzschild radius. Yeah, yeah. Yes. Yeah, yes, exactly. Yeah.
Okay, so we are sort of exhausting our time credit. So one question, yes.
It's to make this fun. It's not really a question, but it's kind of to stimulate discussion, and this is not for the senior people. Like, well, of course, the authors, Pedro the Shadow Master, you are not allowed to answer this. But if you noticed, and Haroldo showed that with the presence of the magnetic field, the intrinsic geometry of the horizon became prolate. Prolate. So it was stretched in the z direction. But if you saw the shadow in the presence of the magnetic field, it became oblate. So the question is why? And you cannot answer now, but we can discuss afterwards. Okay? So thank you.
Okay, so I hope I didn't forget anyone. So let's thank again Haroldo.